I'm very happy. We've already started talking with Dylan. So Dylan, as he mentioned, is an assistant professor in MIT. He received his PhD in computer science from UC Berkeley. And his research focuses on value alignment problem and artificial intelligence. He's been working on a huge variety of areas of research, from theory and robotics and task and motion planning. And as you've already got to see, he has a lot of interesting ideas to share with us today. So I'm very excited to introduce Dylan. Go ahead. Thank you.
Thank you so much. It's a real pleasure to be here. And I'm very excited for this presentation. I think, especially because we've got an appropriately sized group for it, please, I'll invite you to leave your cameras on if you're comfortable with that. I've got the little gallery view up on my screen, so I can still see your faces. And if you want to ask questions, please don't hesitate to interrupt or anything like that. I think, you know, I've got content prepared. If there are no questions, I will certainly be able to fill the time. But I would really enjoy for this to be a conversation. So please don't hesitate to interrupt. And I believe if you raise your hand, I'll be able to see that. Alternatively, if you just unmute and speak up, that would be great as well. All right, and so with that, I'll turn over to what I'm here to be talking to you guys about today, which is a combination of incompleteness, overoptimization, and Goodhart's law. So just kind of going through the different words in the title here. Incompleteness is the idea that we don't have full information about the world. And in particular, we don't have full information about full normative information about the world. Overoptimization is something we'll get into a lot more detail on this talk. But it's the pervasive sort of property that we observe that optimizing for a particular goal or objective, even if it's slightly misspecified, can lead to very, very large, not sort of small misses in terms of the behavior that you get, but actually very, very large differences. And this is related to the notion of Goodhart's law, which we'll get to very shortly. So the first question that kind of unites all of these ideas, and in the case I'll make for you guys today, is thinking about why are incentives brittle? So why is it the case that if I specify a goal or I write down a cost function, it's very easy for systems or people really to take that and go kind of haywire. It's, you know, very hard to predict the response of intelligent agents to incentives. And in my experience, I sort of have run into this, at least where I learned about this was really in the context of robotics. So here's an example of a robotics problem that you might have in which you would like your robot here, this kind of Jaco arm mounted on a table. This is, of course, in simulation. And what you'd like it to do is follow a path identified by these green dots. And the way that you specify this is through incentives. So in this case, we had a couple of different features of the world, like the distance of the robot from the person's torso, distance from their head, distance from this vase, which you don't want to break, and distance from the table, which you don't want to slam into. And what it looks like is you kind of tweak these knobs until you get something that looks like what you want. And in this case, we tweak them, and in these environments, everything looks fine and good. And then you get into a new environment and it does something like this. So this is a great example of kind of brittleness. As you can see, the robot arm is going straight through the vase, which is not exactly what we want. So you could view this as a generalization failure of the incentives that you specified. Another example, which I've used a bunch in talks, is this one here, which is a reinforcement learning system that's learning based on pixels. And in theory, what it's supposed to be doing is playing a boat racing game, which involves going around. You just saw the other boats just went through the window. And of course, the system is not doing that. It's not doing anything close to that. But if you look at the particular method that it's arrived on, it's actually doing a very, very good job of optimizing the objective it was given. And to see that, you can look in the bottom left of your screen down over here. And what you can see is that there's the score function that keeps going up. So what happened behind the scenes here is the system designers said, okay, well, we want the system to learn how to play this game. What reward function should we use? Oh, well, there's this nifty little score component in the bottom left. And we only have access to the pixels of the game, but it's very easy to crop that section, OCR it, and then use that as a numerical evaluation of the quality of different states in the world. And the system then gave the designers actually a very good dose of what they asked for in some sense. And then discovered this kind of ingenious strategy of you could spin around in circles and you could get effectively infinite points because the race won't end. You'll just keep going around, and these little green turbo balloons, it turns out, are worth points. So this is an example of a reward function that I would argue is kind of like, at least qualitatively from some perspective, I would never be mad at like one of my students if they had chosen this reward function for a system. It seems perfectly natural. And yet you get this very peculiar, but also kind of intelligent type of behavior. And we can think of this as almost like a type of disobedience, right? And so this phenomenon is pervasive. You see it all over the place, and it's not new in the context of artificial intelligence. So here is one of my favorite paper titles, and it's titled "On the Folly of Rewarding A While Hoping for B," by Kerr from 1975. And this is one of the papers that really kicked off the study of principal agent problems and incentives in economics. And there's one little clip from the introduction, which I'll read, which is, there are numerous examples exist of reward systems that are fouled up in that behaviors which are rewarded are those which the rewarder is trying to discourage. So this is something that we see in machine learning in practice, and in these types of, it has its roots in these incentives and agency problems from economics. And I'm jealous of Sendil Mullainathan and Zaid Obermeyer for stealing a paper idea that I had thought about in my head, but I just never got it down on paper in time, where they basically took this idea and brought it into the context of machine learning, where they discussed the inequity of predicting A while hoping for B. And I want to give an example of this because it really does kind of round out some of these incentive ideas in a real world problem with real impact and an actual AI system. So what they looked at was basically an insurance company's attempt to determine which individuals are in need of specialized intervention program and which intervention programs are likely to have an impact on the quality of individuals' health. So their goal here is basically, we're going to use machine learning, we're going to predict people that are in need of care, and we're going to try to recommend preventative care to them because that's more effective and more from a cost perspective and from a health perspective. And the proxy that they used was predicted healthcare costs, which is not exactly the same as predicted health values. So healthcare costs certainly relates to health, but there's also the specification gap that you have. So what did they do? They basically looked at a bunch of different patient records over time, trained a system to predict, and then started recommending different care to folks. And what they found, or what Mullainathan and Obermeyer found, was that this system ended up learning a very pervasive racial bias. And that's because the specification gap is there's not like independent noise across all the different patients. There's a very large statistical difference in the behavior of American healthcare patients, which is that there's historical mistrust of the healthcare system on the part of the Black community typically. So what this shows here is on the y-axis, a noisier but stronger signal of health, which is the number of chronic healthcare conditions a patient has. And on the x-axis is showing the percentile of the algorithm risk score. So this dotted line is showing kind of the high risk patients that they're going to recommend extra care to. And what you can see here is for Black patients, you have to get up to almost 5 chronic conditions before the algorithm would identify you as high risk and in need of intervention. Whereas for white patients, that would happen somewhere around 3.5. So this is a really big gap in the performance of the system. And it's related, I would argue, to the incentives that they gave it, which is we're interested in predicting healthcare costs rather than actual health, which again, I would argue from a very first pass analysis, this is a reasonable choice. It just happens to be the case that it's not exactly right. And then in deploying this system, what you see is a large stratification in the number of people recommended for actual care. So all of this is related to a phenomenon that's known colloquially as Goodhart's law, which if you go look at for something in Goodhart's papers that looks most closely like it, he wrote in 1975 that any observed statistical regularity will tend to collapse once pressure is placed upon it for control purposes. So Goodhart was talking about different basically approaches to monetary policy, and was pointing out how once you start measuring something, people's behavior changes, and then what you care about becomes uncorrelated from what you use to measure it. And this is a good version of the form of the perspective, but it's actually not the way most people talk about it today. When people talk about it today, they use this, which is much punchier and I think much clearer, which is that once a measure becomes a target, it ceases to be a good measure. And this appears to be a general phenomenon, but it actually, so this was about a year and a half ago, I started trying to look and find, where does this actually come from? At the time, if you went on Wikipedia, they would actually say, oh, this is from a 1997 paper by anthropologist Marilyn Strathern, which she calls Goodhart's law. But then if you go look at her original paper, so this is the relevant excerpt from her paper, where it does say when a target becomes a measure, it ceases to be a good measure. But if you go down one more sentence, Hoskins describes this as Goodhart's law. So long story short, you can find there's this basically collection of books on accountability in business management, and you can go and look that up and find that Hoskins actually is the person that we should attribute this quote to. So really, when we talk about Goodhart's law, I would argue that what we mean is Hoskins' formulation of Goodhart's law. And I was really happy that I went and did this sort of research, and you could do this as like more of a historical peculiarity. But it turns out Hoskins' paper actually has some interesting ideas that I want to put forward for you guys. And his essay was titled "The Awful Idea of Accountability." And it really deals with this question of where in history does the idea of a measurable target come from? Where here he's thinking about accounting practices within businesses where you set basically targets of certain values that you'd like to hit and then measure people against that over time. And what he identifies pretty clearly is that this is a modern-ish invention that really comes from the late 1700s universities, largely in Europe and England, where initially, if you would go to a professor and ask like, oh, who's your best student? They might tell you a name or something like that, but there wasn't as clear of a record of this. And it was really in the late 1700s where you started to see the practice of grading that we see in schools and institutions now start to arise, where you're doing regular examinations, recording those, and using the combination of those records in order to rank people. And this is really where we see the beginning of organizational practices that build around explicit measurement of performance and the setting of targets and the evaluation of performance against those explicit targets. And all of this draws a lot on some of the philosophy of Adam Smith, where he basically talked about the idea of splitting yourself into an acting self over here on the left and a judging self. So this idea that you have behavior and you have judgments and evaluation, and it's the way that you sort of bring your behavior to align with those judgments that leads to some of the concepts of rationality that we see today. And I would argue that we work hard to operationalize within artificial intelligence. I think if you're familiar with actor-critic formulations within reinforcement learning, this should look very, very familiar to you. So where are we now? Well, we're talking about where the idea of measurable targets comes from. And we're realizing that although it may feel fundamental from our perspective, in many ways, it's more of a newer invention than we might give it credit for. And I think what's interesting then is to take this sort of natural concept and to look at the rest of Hoskins' argument, because his central claim is really that the existence of measurable targets leads to a contradiction, or really implies that you can conflate properties of the world as you might measure them with normative properties of the world. So he's sort of claiming that by writing down a measurable target, you are in practice arguing that you can derive normative properties of the world from physical natural properties of the world. And he argues that this is a contradiction with Hume's law in effect, so which says that you can't actually do this, that there's something extra that always has to be brought into the arguments. And so why am I talking about all of this? It might seem a little bit odd at an AI conference. Well, basically, I would say that this is a first principles argument that we should be wary of situations like this, of situations where we're writing down clear properties that can evaluate every possible state of the world that our system might encounter and rank them as better or worse than the other. And that in practice, this is a very, very challenging task, which I think we're familiar with, and we should be skeptical about claims to have solved it or fixed it. And so this, I would say, is maybe the beginning of a first principles argument for why scenarios like this, which I would call over-optimization, are pervasive. And I think our answer here is going to be roughly that, well, over-optimization appears to be perhaps related to the difficulty of creating the ability to derive the value of a state directly from physical properties of the state. And this is something that I've run into a few times in early work. And so here I'd like to discuss a paper from 2017 where we titled, Should Robots Be Obedient? So I think this fits pretty well with the overall title of the workshop here. And in this paper, we examined a very simple game that we call the obedience game. So in this game, there are two players, the human and the robot. The human's utility is a linear combination of features, so some weight vector dotted with the set of features, 5. And in each round, there are k actions and their associated features that are sampled and shown to both players of the game. The human is going to pick one action, and we'll suppose that they pick that action with probability that's proportional to reward in a relatively standard way. And we're going to suppose that the robot gets to observe this action and then pick a potentially different action. So this is where we're creating the opportunity for disobedience to occur. And then finally, the team is collecting utility from the robot's action. So the person's action is purely informational. The robot is the one acting in the world. And at least in theory, there's no misalignment between the system and the person. They both care about maximizing the person's utility over time. And the main idea in this paper was we wanted to look at two different strategies. First, we wanted to estimate the weights from observations of the action, so treat this as an inference problem, and then maximize the estimated rewards for each action. And the other approach was to just copy the person's actions. So this is to run the purely obedient strategy. And what we observe when we run this is, I think, roughly what you'd expect if you're familiar with these types of models. So what we're showing here is on the x-axis is the number of steps in the interaction. This is basically how many observations the system has made of the person's utility function. And on the y-axis here, we're showing the probability that the robot's action is equal to the person's action. And what we see is it starts off, as you would hope, at least, purely obedient in the first rounds. And after 10 steps, it's dropped off a little bit. And by the time we get out to 100, it's disobeying the person more than half the time. And you can see we're showing here in this dotted line the probability the person gives the optimal action. So the robot is, this is kind of a good scenario from some perspective, because the robot has now gotten to the point where it's correcting for mistakes that the person makes over time, right? Our model includes a reasonable probability the person is wrong, and the system learns to correct from that. And as a result, there's increased utility for the team. So here again, the x-axis is the same. The y-axis is now utility, and we're showing the utility improvement that the robot gets from choosing its own action rather than copying the person's. So here is the rough story for why you might want your robot to be disobedient, right? People make mistakes, you can learn to correct for those mistakes, and as a result, your utility will go up. But I suppose oh yes, question, please.
Hi, thank you, wonderful. This is just a clarification question. So the point here was that the initial guidelines given to the robot were incorrect towards maximizing the reward. Is that what happened?
No, so the robot is observing the person say, in this situation, I'd like to take this action. In this situation, I'd like to take a different action. And it's combining all of that information to build an estimate of the utility function for the person. And then it's using that estimate to select actions rather than just take the action the person asked it to take. And so in this case, you're basically seeing this utility gain because you can learn to correct for mistakes over time.
Thank you.
Great, thanks. Yes, so in this case, things look pretty good. But I led into this with a bunch of examples of robots doing the wrong thing. So you should be expecting me to point out, to pull out, to kind of make a left turn around here somewhere. And that's coming on the next slide. Because what we did next is we brought in some of these ideas of incompleteness, right? A big assumption here is that the robot knows all of the things the person cares about in this situation. And if you change that assumption, you start to get a pretty different analysis. So here what we're showing on the y-axis is that obedience probability from the first plot. And the x-axis is now the number of features that the robot has in its utility model for the person. So on the left, it only has one feature that it knows about. And there are 9 features that the person cares about that aren't part of its model. Right here in the middle is when it has the 10 features the person cares about. So those are the plots I showed you earlier. And then on the right is when we have a bunch of extra distractor features that have been introduced. These 3 different lines show the obedience as a function of the number of features at different steps in the game. So when we start off here, this is step 0. So this is the very first interaction between the person and the robot. Step 10 is this one here, which is kind of our estimate of like kind of an intermediate amount of information. And then step 100 is the far right of those previous plots, where we're kind of roughly at convergence for this model. And the thing to notice is that in the incomplete features regime, the system is far more disobedient than it kind of should be if you look at these middle points, right? So even in the very first round, in the very first interaction, there's a 25% there's only a 25% probability that the system takes the action the person recommended in its first case. And in this case, you might look at this and kind of think that, oh, that has to be a bug somewhere. And it turns out it's not. The reason this happens is because it's very, very easy for the person to take actions that from the robot's perspective are purely dominated by others. So we have a linear utility model, which means that for the one feature the robot can observe, you either want to drive that up to its absolute maximum or drive it to its absolute minimum. And the only question is the relative sign on that feature. So what happens here is the robot's taking one observation, inferring what the sign is on that weight, and then suggesting either the max or the min. And in many cases, that's not the best thing when you consider the full picture. So that's kind of this wonky behavior that you see in the very first interaction. And the thing to notice is that this doesn't go away over time. Right? In this missing features domain, you have these persistent mistaken estimates of reward because the true utility function is just not part of your hypothesis set. It's not something that the system will ever consider. On the other hand, we see a fairly different story when we're in the overcomplete regime. So in the overcomplete regime, we see the same behavior in the first step. When we're in intermediate states, we actually see that the system is kind of more obedient than it should be in comparison to having the correct model. This is because there are distractor features that the system has to rule out over time in order to make stronger inferences about the right action and overrule a person. But when you get to the tail behavior of the system, you can see that for the most part, these have dropped out and you're behaving in about the same way as you would with the correct feature set. And this next plot is a little bit more complicated, but it shows the impact of this on the utility for the team. So again, we've got the same x-axis. The y-axis is now utility. And what we see is that in step 0, we have lost utility in the incomplete regime, no change in the overcomplete regime. For these intermediate steps, we still lose utility in the incomplete regime, and we lose utility in the overcomplete regime because we're leaving opportunities to usefully disobey the person on the table. And then finally, when we get to the tail behavior of the system, in the missing features regime, we're still consistently leaving utility on the table, but in the overcomplete regime, we've ruled out those extra hypotheses, and now we've roughly figured out what the person wants. So the basic takeaway here is that there are real opportunities for disobedience to provide utility in the sense of correcting for mistakes. But when you're designing systems that are going to overrule the person on whose behalf they're acting, then you want to be very, very careful about this incomplete regime. And if you combine that with the first principles arguments of Goodhart's law and Hoskins, you start to become skeptical at your ability to provide an overcomplete specification. Right? You should expect that in many cases you will end up in this incomplete regime, and you want to be, so this suggests being very, very careful about these situations and building in sort of strong regularization there. And that's because these arguments, I would say, suggest that incompleteness is a source of fundamental uncertainty in the case of AI systems, right? So here's a rough picture of a system designer who has some goal in her head represented as R star. And you might say that this person may leave out features of the problem specification. I think that in practice, you should expect that the system designer will leave out some important features of the problem specification. And you can connect this to the idea of incomplete contracting, specifically within economics. And so here's a paper that I'll throw up here as a reference if you want to go read more. But what we do in the paper is we go through the reasons why contracts are incomplete and don't always specify exactly what should happen for every possible state of the world. And we identify parallel weight reasons for why rewards are misspecified. So for example, when you're writing a contract, you didn't realize that, say, COVID was going to come around and was going to completely change your ability to provide goods. And that might be something that's not well accounted for in the contract. And the same thing is true in bounded rationality as you're thinking about all possible contingencies that a system might be into. There's challenges of costly cognition for, or drafting, right? You have to pay lawyers to write contracts. Same sort of thing when you're designing AI systems, you've got costly engineering or system design. And the main takeaway from this is that I think there is both value in studying the ways that contracts are incomplete, and also value in ways of studying how we build contracts in order to manage that incompleteness, right? Contracts don't only specify, here's who gets paid what for every outcome. They also frequently specify things like, here's how we will mediate disputes. Here is the way in which we will handle issues that arise that are unexpected. And in the design of systems that are going to have the capacity to be disobedient, that's a crucial component, I would argue, of any reward specification or system specification. All right, so now I want to kind of, so far, what have we done? Well, we've talked about some fundamental concerns you might have about your ability to completely specify incentives. We've argued that it can go wrong with a particular example. And now I want to argue and sort of present some results from a 2020 paper, which argues that actually there are sufficient conditions we can identify in which you should expect over-optimization not to just lead to the wrong outcome, but to perverse and very, very suboptimal outcomes. So in this case, we had a model of misalignment where we've got a system designer that has a goal in her head, and she specifies a proxy of some kind. That goes into the robot in some way, which then maximizes that, and we'll model our system as producing a sequence of states that make incremental changes to the world. So our assumption here in our model of incompleteness will really be that this true reward function depends on some set of features that live in RL, whereas our proxy will depend on features that live in some RJ. And we'll enforce that L is larger than J in some way. And then finally, to prevent you from sort of moving around arbitrarily in this space, we're going to introduce a shared resource constraint across all of these features. So an example problem that we use in the paper is one of a simplified platform management one for something like Facebook or YouTube or Twitter or something like that, where in this case, your features might be the probability that someone will click on a piece of content, the level, maybe a more sophisticated measurement of engagement. You might have features that depend on the overall prevalence of hate speech within within the community, and then maybe kind of a nuanced description of overall community well-being or something like that. And our shared resources in this example, you can think of as being user attention. So people have finite attention. We can only think about so many things at a given time. Or you can think about it as being the space in the feed, right? If I choose to allocate some pixels to one particular piece of content, I can't use it for a different piece. And so we wrote out an example. We picked some values for the actual reward function. We picked a proxy. We optimized it with something like gradient descent, making sure that we obey the shared resource constraint. And we ended up with something that looks like this. So here is sort of the number of steps that we've made to optimize. This kind of how big of a move we're making in the state space. Here we're showing how much the utility has changed from some starting state. And what we can see is that proxy utility goes up and up and up, as you would expect. We're optimizing that. And true utility goes up, reaches some peak point, and then starts to fall off. And it turns out that if you pick any combination of two features to include in the proxy, you see exactly the same result. Where here we've looked at all possible combinations of these incomplete proxy rewards, and you see that some of them do very poorly immediately, but they all eventually have this behavior of going up and coming down, and then being worse off than when you started. And what we sought to prove is to identify what are the conditions under which you can expect this to happen. And so just a little bit more detail on our utility model. Our state space is going to be states that have a lower bound on features, but no upper bound. And resource use will be represented by C of S, and be capped to be less than or equal to 0. And all features use resources positively, in the sense that the partial derivative of resource use with respect to each feature is greater than 0. And our utility function is roughly the same, in the sense that we're going to think of increasing each feature as a good thing. And so the partial derivative of utility with respect to each feature is also positive. So these are not really features in the sense that you might use in like a regular robotics setting. These are more like different objectives. So you can think of the different features here as really being different objectives out of which you construct your overall goal. Our proxy model is about the same. It lives on a subset of those features. And our proxy metric is just going to depend on those measured features that are included in the subset, and we'll still have that the partial derivative of the proxy with respect to each feature is greater than 0. Our optimization model is one of incremental optimization. So we think of states as a function of time. We start at some value S0, and then we integrate this rate function that depends on our proxy objective. And we'll make the assumption that this optimizer eventually gets to the optimum point of the objective it's given. So in the limit, as time goes to infinity, the states sequence we get to reaches the maximum state across all of the proxy objectives. And now that you've all borne with me through all of that math and notation, we can get to the payoff, which is that we're able to show the following result. So any fixed proxy objective that depends on fewer features than you care about eventually loses utility. And so what we mean by that is, suppose we have a utility function, R star as defined before, a proxy, R tilde as defined before, and a state space as we just went through. Then let S tilde star be the best state according to the proxy. We get an equivalence between the following two properties of the world. If the set of states intersected with the set of states where true utility is larger than some value R minus, if that's compact in the sense of a metric space where it can be put inside of a ball, so we can kind of contain all of the states that are better than a certain minimal value, then this means that there's some value B minus such that if our environmental limits are lower than B minus, then the amount of utility we lose between the optimal state and the optimal one we get to within our proxy is greater than R minus. So this says that if you have we've identified a compactness property, which says if all states better than this R minus value are contained within a ball, then this means that we are basically relying on external factors in the environment to prevent us from optimizing to the point where we lose at least that much utility. And this idea is a property we call the compact upper contour set. And it is definitely a little opaque for me. The student I was working with was one of these kind of like math whiz people. And so he came up with this really general condition. But it turns out we can think about this as being a stand-in for a bunch of sufficient conditions. And I would argue that these are conditions under which we should expect over-optimization to occur. So first, we have decreasing marginal utility per resource allocated. So this says that as we allocate more resources to a particular feature, then we get less utility per resource we allocate. So if I allocate one resource to improving engagement, let's say, that's going to be less valuable than 1/2 times allocating 2 resources to, more valuable, right? So as I add more, we see diminishing returns. And then the other condition we have is additive separability for the constraints and utilities. So if you can break this up into your reward function is something that looks, roughly linear across all of the different features of the state, and your resource use is also linear across all the features of the state, then you have this, as long as your final condition is basically that there's no sort of degenerate resource use or anything like that. So everything has to be strictly greater than 0 in order for all of this to go through. So to me, I'm actually pretty excited about this result. I think it allows us to start taking some of the more informal arguments about Goodhart's law and the difficulty in specifying incentives, and allows us to start to identify properties of environments and decision settings under which this is expected behavior in many ways. Now, what does this mean for the design of AI systems? Well, I think there's kind of 2 ways you could try to get around this in theory, and both of them are things that people are roughly looking at. So one is an approach that might be called impact regularization. So you try to have loose dependence on all of the features through some sort of generic distance function that measures distance in your original feature space. And then you maximize your proxy and keeping in mind some measurement on impact or penalty for that. And another approach is to think about interactivity. So if you have more than one proxy reward, if you're able to update that over time as the world evolves, you can also get some better results. And so this impact regularization, it's not hard to see if you're able to tell the system don't change the world too much, why you can make positive progress. Of course, it limits your final utility you can get at the optimum, but that's not too bad. For interactivity, we add a little bit more math to show that this can be done in a way that's provably safe. So we assume that there's efficiency, so the system's not just going to destroy resources. And we basically make use of a property that we call attribute sensitivity. This is basically the partial derivative of utility with respect to resources allocated along a particular feature. So this is kind of telling you, if I allocate 1 unit of resource to this feature, how much utility do I gain from that? And then there's a pretty simple strategy, which is we order the attributes of the state by sensitivity, and we define our proxy on the top J attributes according to that sensitivity. So kind of we're saying, what are the features that would be most useful to allocate resources to? Those are the ones we should include in our proxy. And then this guarantees that there's a neighborhood of states where we have local alignment between the proxy reward and your true rewards. And so you can imagine an interactive strategy where you're constantly updating your features in order to make sure that this property holds. And then that guarantees that improvements in your proxy will be reflected in the underlying utility. As I mentioned, an important question here is whether or not you'll reach the optimal state according to your true utility. And on their own, impact minimization and interactivity don't reach that. Impact minimization will reach the maximum state such that states that aren't included in your proxy are set to their original values, which naturally caps performance. And interactivity is going to reach a property where the top J+1 sensitivities are all equal. And in order to have actual optimum, you'd need this property to hold across all of the features of the world. However, you could combine them if you wanted to have a guaranteed optimality from this interaction. So actually, the first approach is remarkably simple, which is you just take random attributes put them in your proxy and use impact minimization. So this says, okay, we're going to optimize over random sort of goods in the world, random features that we care about. And we're going to include a cost which says, don't change things that we're not telling you about. And the other one is to make sure your proxy contains both the highest and the lowest sensitivities, and then use impact minimization as well. And what this looks like sort of intuitively is telling the system, what we want you to do is actually engineer or facilitate a transfer of resources between these two measured attributes of the world, and do your best not to change anything else along the way. And you can try out all of these. We tried them out. I'd advise you to go look at the paper if you're curious to see the details of all of them. But I think I'd like to conclude here by saying that if you look at these ideas, you should see them deployed in AI systems in the world. And we went out and we looked at different ways that recommender systems have actually been modified in order to better align with different value systems. And what we see is a very clear three-step process that goes on at a bunch of these companies, where first there's an identification step. This is where you basically figure out bad things that are happening on your system and you create a concept to represent that. So this might be, you realize there are links people are clicking on and they're not getting much value from. So this would be the invention or the discovery of clickbait. And so that's something new that happens with internet platforms, and you have to basically come up with a name for that and be aware of it. It might be becoming aware that your system is heavily upranking different videos of conspiracy theories, or that the way you're optimizing over tweets in order to recommend them to people is basically instigating a lot of harassment of different people on the platform, because that's a highly engaging signal. Then once you've identified the concept, there's a step to operationalize it. And this is where you develop a concrete procedure to identify instances or measure the prevalence of that abstract concept. And in this case, for something like clickbait, this might be something like watch time, where you keep track of how long people spend on a site before they come back to the platform. And in many cases now, this is something like a machine learning system, where you label different categories of the behavior and use that to create an operational definition of these different features. And then, of course, the final step is to adjust the system. So you modify the recommender system to increase or decrease prevalence of that concept based on how you measure it. And this might be done in an old-fashioned way by incentivizing employees directly. So those are definitely agents involved in the system. In many cases, this is done through using these features and measures to figure out what different product changes to launch through A/B tests. And then the final thing that happens is you might include these metrics directly within the optimization objective for the system in order to figure out which optimizations you really want the system to have, and kind of incorporating these in a holistic way. And so the key implication here is that we should be optimizing industrial AI systems to actively identify unspecified qualitative harms and to rapidly adjust system behavior accordingly. And I think in the design of systems that could be disobedient or might behave in ways that disagree with your stated goals in the immediate sense, this is a really, really crucial property to be thinking about and managing. And with that, I think I'll ask, how am I doing on time here, Ruth?
You're doing great. I think you have about 5 to 10 more minutes.
5 to 10 more minutes. Okay. So then I will just conclude with something that is actually a bit related to some things we were discussing earlier in the talk, which is if you're thinking about this in the context of platforms and social media, then, well, what is this? Well, this is hopefully the elephant in the room. And by that, what I mean is we recently had within the US, the example of, this is Frances Haugen, the whistleblower for Facebook. And we had this large leak of files. And I think the main thing to take away is this sort of opening line, right? Facebook knows in acute detail that his platforms are riddled with flaws that cause harm, often in ways only the company fully understands. And what this means is, at least we're thinking about AI systems and disobedience and kind of the companies that manage them. Sometimes knowing about the problem is not enough, right? You have lots of challenges that arise from a multi-stakeholder world where you also need to have the ability for systems to reason about harms that might occur to other people and to bring that into account. So to really simplify things, consider a robot that gets this is an example from concrete problems in AI safety, and consider a robot that gets a large reward for bringing these boxes from one side of the room to another, and suppose that there's a vase along the shortest path to get from one to the next. Now, if the robot is only maximizing and only cares about this reward, it might go through, knock over the vase, break it, and cause a lot of harm. A person, on the other hand, might be, in this sense, kind of, somehow like cleverly disobedient in that it will take an action that is different from its specified rewards and go around the vase. And why does this happen? Well, there's two things that the person brings to the situation that are crucial for this reasoning. The first is that they know, from a physical standpoint, this is positive information about the world, that if I walk through the vase, it will fall over and break. That's a prediction problem. AI systems still have a long ways to go before they're better at that. But to that, they also bring contextual normative knowledge that there is a negative cost for breaking the vase. And the question is, where does that come from for a person in this situation? Well, it comes from the sort of understanding of the broader normative context that they're in, which is, if you are doing this, you may get taken to court and you may be forced to pay damages for the harms that you cause. Or other people that you work with or in the building might get angry at you, and that would make you feel bad or be something that you don't want to have happen. And so this is to say that human contracts rely on tons of external structure in order to function properly. What was it reasonable to think that the parties had in mind when they agreed? And this reasonable point is something that isn't defined purely internally. This is something that's defined by society at large, by our institutions, by our norms and our laws. And so what this suggests is that, especially in the context of designing AI systems, I would argue in general, but specifically with the idea that we're thinking about the places where they might want to behave differently than they've been asked to do, it's crucial for us to consider this picture between a system designer and their system, and to bring in the idea of external groups that have opinions and beliefs about what's going on, and design our systems to include external affordances for these groups to provide external input into the rewards and incentives for these systems. So the incentives that we're using need to be crucially shaped by external parties. And you could imagine this occurring in several different ways. Some might be allowing systems to predict the approval or disapproval of different groups of certain behaviors. Some of it might be more explicit in the sense of allowing external parties to provide metrics and proxies of their own that are actually incorporated directly within the system. And I would argue that this is kind of the final place where I would want to leave you guys on basically that the design of systems, as we're thinking about misalignment with individual principles, really should think about ways that we can include incentives from broader society and basically include societally constructed values in the design of system in a systematic and regular fashion. And with that, I think I'll conclude, and it would be great to take any questions that you might have. Thank you so much.
Thank you, Dylan. That was truly fascinating. I have lots of questions, but maybe anyone else wants to start?
I'll jump.
Sure, please.
Dylan, great presentation. You bring so many things into this framework. It's fascinating. I must admit, I was really hooked when you talked earlier about the notion of measurement and how we can get trapped in regards to using certain measures and not understand some of the impacts of them. I ran into this in some sense in a real world way, and I'd like to just briefly mention to you. So when I was a PhD student, I started a repository for my research community, and it became known as the ECI repository for machine learning databases. And it's been used today. It's been cited over 20,000 times. So this repository was one of the first of its kind, in which it allowed for researchers to grab a hold of databases other people were using so as to test their systems. So you see where I'm going with this. The problem is that it was an example in which people were designing, well, really pursuing their research so as to, in some sense, get credit for how well they did on this repository's contents. And then though other people would eventually look at this and say, oh my gosh, that's such a waste of time. You really need to be thinking about other problems or how these databases are constructed or focus on certain, well, there are a billion reasons, but it just fit into this notion of overemphasizing a metric. In this case, it's more societal, but I hope I conveyed what I was trying to.
No, I agree. I think, I mean, benchmarks and measurements are incredibly powerful. I think one of the things that maybe some of this discussion or some of my presentation could have emphasized a little more perhaps was measurable targets are an incredibly powerful paradigm for aligning group behavior. I mean, in many ways, arguably, it's an invention that allows modern complexity to exist, right? I think, if we think about organizing the behavior of a company, there's a lot of sort of individual information sharing and goal sharing and all of that, but it really helps to have a number or two where you all agree when this number goes up, that's good, and when it goes down, that's bad. And that can be incredibly useful as an informational tool for getting people. And I would argue this is like one of the central insights that allows AI systems to work. And at the same time, that's kind of why we need to be so careful about the places where our measurements can bias us, and where the things that are hard to measure or that are incorrectly measured really do have downstream impacts on systems.
Thank you.
Yes, thank you. Kentwan, I think you're next up.
Yeah, so kind of piggybacking on what you just said there. And so you talked about how having these incentives that are based off of metrics then cause their own issues because they're probably poorly formulated and things like that. But then at the end, you had talked about how it's important for then external groups to then also add their own metrics and their own incentives. And I can just see this as just being this like ever reoccurring thing of adding more and more garbage or illy formed things to these systems. And the question there is like, how do you think that should be appropriately done to take into account external forces that might have conflicting value points or conflicting viewpoints and things like that?
Yeah, I think my first answer is to say that I definitely don't know if you figure out the solution to that problem, please let me know. I would love to hear it. I think part of the idea here is that we want both rapid iteration on metrics. We want if you think about this as a control system where your control variables are specifying incentives, you want to really reduce the delay in how long it takes from something starting to go wrong up until you have measurable versions of the ways in which that's happening, up until the ways that those incentives can be incorporated. And so I think there's a lot of value in reducing that delay. I tend to think that having a really broad diversity of metrics is generally a good design strategy. So being able to have metrics that are maintained internally is good. Having metrics that are maintained externally that incorporate other values at least gives you sensitivity to those things that other people care about, and gives you more opportunity to rapidly design it and iterate on top of that. So I think of it as we will never have a full picture of everything that matters, but the more quickly we can refine that picture and create structural ways to incorporate these different failure modes and information and sensitize systems to that, if you will. I think that gives us a good way to move forward. And in many cases, I mean, there are lots of interesting technical questions around how do you build representations of value and practically, how do you approach that as a technical problem? But many of the challenges we see right now are more political than technical on this front, right? There are lots of ways of measuring harassment, or ways of measuring different types of what constitutes a conspiracy theory. But the challenge in getting that to impact real systems is, right now there's basically corporate executives or business people who are making decisions at the granular level of like, oh, what is the official YouTube policy on this? And I would argue that what you should say is, well, let's have a large diversity of these metrics, and then work on designing systems that are sensitive to that diversity and can respond to either user choice or community choice on that. So it's not about blinding systems to it, but it's about making it easy for lots of groups to provide this feedback. And so even if you might choose to not prioritize those metrics at different points in time, you at least have them there, you're able to track them, and if you start to run into issues, you can start to adapt them. Right? I think of this as sort of a generalization of some of what the court system offers the rest of society, in the sense that if you engage in a contract with someone, there is a dispute resolution mechanism that you both can leverage in order to identify that. I think that external definitions of metrics to be used in incentives are sort of a generalization of that idea to having external groups that are maintaining definitions and adapting them as the world changes. And I think that could be very valuable. But I also agree that you might think that it's a bit more garbage in, garbage out than you'd like. And there, I think it's just, at a minimum, you could use a large diversity of these incentives as an impact measurement score, where you try to say, well, this is a way for me to identify when I might be causing problems, and then use that to go in and investigate. Also add here that another direction of research that I don't have any concrete ideas on yet, but I think is suggested by some of this analysis, is basically tying the rate at which you optimize a metric to something about the rate at which information about your true goal sort of flows into that. So you can think about it as as I optimize, I sort of learn different ways to move the world so that it better aligns with this particular measurement. And I should kind of regularize my optimization, if you will, based on the rate at which that measurement and metric is adapting to capture my notion of truth or value. And if these two get out of whack, then that's probably when you start to see this over-optimization. And the results I showed can be thought of as sort of the extreme version of this being out of whack, where you take one fixed measurement and optimize that ad infinitum.
So I would like to maybe continue this idea that Cantwan basically, he said there's something interesting, that it's like the story with turtles all the way, it goes turtles all the way down, that you just have more and more metrics. So you talked about the ball, that is, you have a compact set, and then you want to be outside of that ball with additional metrics. Maybe when you leave the ball, there's a way to use things that are not metrics. So you talked about the court system, that basically it doesn't give you additional reward, it enforces, it does something else, it gives you an alternative in a sense. So it's no longer a metric that you optimize when you have crossed some line. Are there, and I know from your work that you have been looking at other corrections and things that can be incorporated into a robot. And when disobeying, would you say that maybe you don't want to provide more metrics, but you want to provide policies, behaviors? Do you have some insights on that, maybe once you cross this line?
Yeah, I think, so I'll say, when I'm thinking about metrics here, I'm speaking quite generally, in the sense that So for the court case, we might think of that as the metric in the way that impacts my incentives is I have a prediction about what the court will do if this happens or that happens for counterfactual reasoning. I do think well, let's think about the machine learning way to try to define some of these metrics that you might use. In many cases, that's sort of like, supervised learning is almost like a very, very scaled down version of imitation learning in some sense, right? Where you're saying, in this case, here's the value I would give, and in this case, here's another one. And so I think different ways of providing information are crucial. And I would say that, in some cases, it's much easier to provide direct actions and supervision of, oh, in this case, do this, and in this case, do that. In others, I think that it's, one of the things that's useful about metrics, one of the reasons I like to think about reward design is they can encapsulate behavior in a bunch of situations. And they sort of serve as almost a steering wheel on top of different types of policies. So if we think about like a robot arm, no person can ever actually give demonstrations to a 7 degree of freedom robot arm. It's not something that we're physically capable of doing. Even if you had 7 different knobs that you could turn, it would be really difficult. So instead, when we give demonstrations, we guide the system through a sequence of waypoints, and then we define a time-varying objective of moving between the different waypoints. And so I really do think reward functions are the natural language that we use for this. But I would say that what they mean and the particular context in which they're provided is what allows you to draw inferences and sort of extrapolate or not sort of more effectively. So maintaining uncertain, I would say that all right, so that was a little bit rambly. In summary, the language in which you provide information is important. Most things will in practice be turned into some sort of metric when they're incorporated into the incentives for systems, because that's just the way that we tend to program them these days. A really powerful tool there is to take into account context and maintain uncertainty about the overall objective. And I think that uncertainty gives you an opportunity to fuse information from a lot of different sources. And here I might point to Smith-Millie's paper on implicit reward rational choice as a bit of a unifying framework for some of these feedback approaches.